Hello everyone. So today we will proceed to learn about week 9 content. So far, Chakrabarti has taken design using root locus. So we know there are two different categories we have been learning, right? That is time response categories, and another one is frequency response category. So, as before the exam, as I have differentiated these two, we have been using a tool like root locus under time response categories to analyze the system in time response domain. This kind of tool like root locus will be helpful to analyze the same system in different domain like frequency response domain. It's another representation of the same system. We use Bode and Nyquist, right? So these tools are only for analysis. Then comes the control perspective. So ultimately, we want to control the system. Overall Venn diagram or objective of our work is to develop a controller or control a system. In order to control a system, we should know the nature of the system, right? That's why we use tools like analysis. First, we need to do the analysis. Based on the analysis, we should know the nature of the system. Then we apply proper control to control the system. That's the objective for our entire course, right? So far we have been seeing uh, tools like root locus for time response representation analysis tool and Bode and Nyquist for the frequency response. Now we started applying, once we find the nature of the system, we want to control the system using design. This comes under the control perspective. This design compensator, designing controller kind of. So here we are most probably use compensators as a word instead of controller. Okay. Both are interchangeably same, but for particular nature of control we use compensator as a word. We'll explain in detail. So as explained before, this compensator design can also be taken out in two domain, that is time response again and a frequency response. So here yesterday or the last week, Chakrabarti Jada would have explained you about designing systems or compensators using root locus method. Now I am going to take the same for same kind of systems, designing compensators using Bode plot, but there is no design using Nyquist. Only Bode plot is there. Why we didn't have this kind of topics for the quiz exam is, even though you have week 8 inside your quiz exam, we didn't have this topic as a broader mark scoring tool because this is extensively large to handle data and coming up with the final answers, because this is extremely trial and error method. It is not a unique method to do straight away problem solving things like there is no fixed formulas for universally that is applicable. It's trial and error based on your system's design. Sorry, it's completely trial and error based on your system design. So that's why we didn't keep it inside your quiz, but we are going to conduct a design assignment that is MATLAB based on these two. So your design assignment that has already been published, design assignment 1 will be considering using root locus, and design assignment there will be design assignment 2. It carries design of compensators using Bode along with another question from state space, which is from week 10. Okay. So these design assignments is a practical assignment where you will generate your own code in MATLAB and submit the report based on the questions and along with the MATLAB code. That's how we design your design assignment. I will instruct you how you can submit it. Please look it carefully. I will do it at the end of this session. Okay. First, I will give a broader introduction about this design using compensators. Design compensators using Bode. Now we are going to see this. Fine. So, in general, compensators can be categorized into three categories. One is lead compensator, lag compensator, lag lead, or lead lag compensator. Both are same. Okay. Lag lead lag. Anything can be called. It's a combination of lead and lag compensators. So, as I said, compensators are generally controllers, right? So, what do we do while designing a controller? We have already done PID controller design. What we did, we have kept a controller in front of the plant to control the system according to our desired information, right? We will take a feedback out of the system as a y, and we will give a reference, and this error will be calculated here, and based on the error the controller gain k will change here. Based on the controller's nature, it can be kp only, or kp plus ki by s, or kp plus ki by s plus KDS, etc. So there are different types of controllers. I'm considering a common proportional controller, so I'm considering only K here. So based on that, this KP will change, or the nature of this plant will change. And ultimately, your ultimate final response will be controlled to reach a steady state value instead of having a steady state error or some too much peak overshoot, time response behaviors, improper time response behaviors. For example, peak overshoot more than 20% or something. So we have designed controllers so far like this. Here we are going to do the same thing, but by analyzing the system using the Bode plot. So Bode plot has two categories, right? One is magnitude plot, another one is phase plot. So in designing compensator, the first step is you will be given a system. The second step is you will analyze the system using Bode plot. Then you redefine the Bode plot by designing a compensator. Okay, how this works? For example, I have a system. And this is my set point one. I'm expecting my system to give a very less overshoot, and with fewer oscillation, I want it to settle at the settling point. This is how I want my system to be. But what happens is that because of the nature or any external disturbance or something, my system is behaving like this. Okay. It has high overshoot, and it is not settling at the settling point, set point, and it is having some minute steady state error. So there are issues in both transient side and steady state side here in this example. Okay, I want my system to behave like a green color, but it is behaving in red color. So now what I want to do, I want to bring this red somehow closer to the green. Okay, how can I do it? I have to make some changes in my system such that I will introduce a controller or a compensator to my system, so that my compensator will regulate my system to meet the desired requirements. That is to bring down the red graph to green graph. For that, first I need to know why the red graph is like this, right? That's why we are using this Bode analysis. This Bode will tell you, if you plot a Bode for this red plot, this is magnitude, this is phase. Okay, I will encounter something like this. Maybe like this, and my face is like this, something. Okay, not really meaning anything here, just a random diagram. So when I see the phase margin and gain margin, this is gain margin, this is phase margin, right? So when I see this, so it's nearly not in my desired way. So what I want is that I am analyzing the body of green also. It is like this. It is like this. If I analyze the body for both red and green. So I understood this is the issue between the red and green. So I want to bring my Bode magnitude plot from here to here somehow. I want to shrink it inside and I want to bring down my phase plot from here to here. That's what I understood from this. So for this difference in between these categories, I am going to design a compensator. So this compensator will act along with my plan to bring my body from undesirable place to a desirable place so that my time response or the output response will be good or the way I expected. Is it clear till now? Why are we doing all these things? Any doubt in this? If yes, I will proceed further. Okay, fine. So that's why we are using all this compensator design and all. First, before solving problems, we need
Excuse me,
to,
ma'am.
yeah,
Can you explain both the diagram, this upper, the body plot,
this one.
and the role of the compensator used in here?
Okay, I will explain.
From
So,
the starting, I think this graph, the red and green graph. Yeah.
okay, fine. So I have a system and I'm giving some input and getting some output out of it. So consider this as my output. This graph is my output. So I'm expecting my system to behave in a green line. So I need a very less overshoot and it should follow my set point precisely. There should not be any steady state error. This is my desired outcome. But instead, since there are some issues externally and internally because of disturbance or external measurement issues, my system is behaving in a red curve way. So I'm getting output in red, but actually I want it to be like a green signal. Why there are this much difference? That's what my question is. So I want to bring my red curve near to the green curve so that my system will behave according to my requirement, right? So for that I want to design a controller, but I don't know how to design a controller. How can I design it without knowing how it is behaving, right? That's why I'm using a Bode plot for both the systems. When I plot Bode plot for both output signals, for my desired signal and also the system, whatever output the system gives me. So I found that this red is like this, but the green's gain margin and phase margin is far lesser than the red's one. Then I understood that if I make my Bode plot nearly equal to the of red nearly equal to the green, then my actual output will shift from red to green, right? So any of the one thing will happen if I make some control changes. So that's how Bode plot is helpful for us in designing a controller, and how I'm going to bring this red face margin to here, how I'm going to shift the red towards green, and here the shift the face plot of red towards the green. That's where I decide what to do with the compensator. Based on that, there are three different types of compensators, whether you want to shift your magnitude part to right or left or up or down. So based on that, we have to choose the lead lag and lead lag compensators. I will tell what will shift to the right and what will let it shift to the left. Now the overall idea is I have a system, but my system's output is not desirable. I want to pull my undesirable characteristics towards the desirable characteristics. To do that, I am designing a compensator. To analyze why my system is like that, I am using a Bode plot. Is it clear?
Yes, sir. Yes, ma'am.
Oh, right. So as I said before, we have in this graph, there are both issues, right? Transient is also a issue, steady state is also a issue. There are sometimes only transient might be the issue. For example, there will be big overshoots, but it will settle at the steady state value or set point properly. In some time, in some type of systems, the overshoot will be or the settling time will be slow, but it will have some steady state error. So here the issue is transient response is the issue too. We have to fix this transient response. Here we have to fix the steady state response. But in some systems, as I explained before, there might be two issues. Or both the transient will be an issue and also a steady state error. It will have undesirable transients and also some steady state error. So here we need to fix both transient as well as steady state error, right? So now, if you choose a lead compensator, as I said, there are lead, lag, and lead lag or lag lead. Okay. I will use any one of this configuration. So if you use lead compensator, in general, lead compensator essentially yields an appreciable improvement in transient response and small change in steady state accuracy. This helps more towards your transient, less towards your steady state. Like it's not bringing it down, I'm saying this concentrate more towards your steady state. I will like this. The slack compensator concentrates more towards your steady state error. Lead compensator concentrates more towards your transient error. But how lead lag works, this will concentrate both on transient plus steady state. So we will apply. If my requirement is to improvise the transient, I will go with lead. If my requirement is to improvise the steady state error, I will go with lag. If it is both, I will choose lead and lag compensate. This is how we choose compensators. This is one point to remember. The next point is what are lead lag and lead lag compensators. So if you see lead compensation. I think Jada would have explained this before. Let me revisit it. Your lead compensation will look something like this. Kc is a compensator gain. S plus 1 by T divided by S plus 1 by alpha T, where alpha will lie in between 0 less than or less than 0 less than alpha less than. The next thing is lag compensation. Your lag compensator will look like this. K C S plus 1 by T divided by S plus 1 by beta T, where beta is greater than 1. You should remember this. It's actually alpha. It's not beta, is not a separate thing. It's actually alpha, where if your alpha is in between 0 to 1, this region, if your alpha is in between 0 to 1, then it acts like a lead compensator. The same compensator, same system, same controller will act like a lead compensator. If it is greater than 1 from here, it will act like a lag compensation. But to avoid ambiguity, we are using different variables here. Instead of alpha, I am putting beta, but both are same. Please remember this. Okay. Then how come it is lag lead? It will compensate. It will act like a lag lead if the alpha carries all 0 to greater than 0 something. Clear? So this is how your lead lag will
Excuse,
have.
ma'am.
Yeah.
the lead lag, it can alpha can be 0 to infinity or to a finite number.
Uh, it cannot. No. To up to. Okay.
It should be
Uh,
finite, right?
it should be finite. Yeah. Correct. Yeah. So in your lead lag, we will have this kind of representation: xc s plus 1 by t divided by s plus 1 by 1 minute. So like that or hold 1 by alpha t and s plus 1 by t divided by s plus 1 by beta t. Same, where alpha should be in between 0 to 1 and beta should be greater than. That's how your lag compensator or lag lead compensator will work. Okay. Now, how each compensator will look in terms of its body or representation, mathematical representation. Okay, let me take an example and we will deal with that. I will use both MATLAB and this one because the assignment will be in MATLAB to help you with keywords. I will use that. I'm starting with an example. We will revisit the rules because only telling the rules won't make any sense without showing how it works. So this is an open loop transfer function as it has only g of s. The question is, it is desired to design a compensator. We have to choose which compensator it is based on the requirements for the system. This system so that the static velocity error constant kV is 20-second inverse. The phase margin is at least 50 degree and the gain margin is at least 10 decibels. Okay. The question has given a open loop transfer function for a system and they are saying make the kV is 20 seconds per inverse and the phase margin should be at least 50 degree. So if PM should be greater than 50, gain margin should at least 10 decibels. BGM should be greater than 10 decibels. That is what the question requirement is. So in order to see this requirement, first you should know whether your system has this requirement already or you need to design a compensator. To check that whether your system is already meeting this requirement, we are going to do the Bode plot and the analysis part. So these both we will get it from the Bode plot and this we can do by hand, right? KV, you can equate it with the KV formula and you can find it. So how do you find it? kv equal to limit s tends to 0, g into gc. Usually the forward path, everything we will consider, right? So here g into gc.
Then there will be S, no?
There
S
will
into GGC.
yes, where?
KV equal to
Kv, yes, yes. Yeah, you're right. Okay, fine. Um, 1 minute. Yeah, I am now considering some is equal to gain, just to find the gain value to start with. How to start? We are not assuming k equal to 1 as we do in Bode plot. Now we are considering which k I should choose so that my kv is equal to 20 seconds. That's why I'm choosing it like this. 4 divided by s into s plus 2 into k. So s tends to infinity, limit s tends to 0. Yes, yes will get cancelled. 4k by s plus 2. If s tends to 0, this will be 4k by 2 equal to 20. K equal to 10. Right? So my k, initial gain k should be 10. So that I will get the steady state error value, that is kv equal to 20. If my system is 4 into 10 divided by s into s plus 2, if I apply or find a velocity error constant for this, then it will be 20. That's what the meaning behind this calculations. Okay, first we have found how my system should start with. So I am rewriting my system. My entire g of s will be 40 divided by s into s plus 2 instead of 4 by s into s plus 2. Now, fine. So now I'm going to see if I have enough phase margin and gain margin. I will switch to my laptop. Slowly. So we have 40 divided by s into x plus 2 is my system, right? So I'm telling MATLAB that how to consider my s, that is TF of s. If I put like this, whenever I write a transfer function as it will take it as a transfer function is. Not like it won't throw any error like that. 40 divided by s into S plus 2. So this is my system. Okay. If I print my system, it will show 40 divided by S plus 2 plus 2S, or S into S plus 2, say. So now I want to analyze what is the Bode plot giving to my system. So the Bode plot shows so if you want to see the phase and gain margin, you can right click on your Bode and go for characteristics, all stability margin. Choose all stability margin. It will show you your phase margin and gain margin of your system. Otherwise, you can also print using the keywords margin for your system. It will also give you. So from this figure, you can see there is no point in the phase plot like this, right? Blue point. The blue point in the magnitude plot represents the gain margin, but it is not there. So we can understand the gain margin is infinity here if it is not showing here. But here, if you click on this, your phase margin is 18. So here you can see this is your phase margin. To do this, I just wrote a line, right? Bode of your transfer function. Bode in square curvy bracket inside your transfer function should be mentioned. Right. You have a infinity gain margin and you have a 18 as your phase margin. Right. Now I am writing it here. Gain margin of my system is infinity. Phase margin of my system is 18. But the requirement is, how much is the requirement? You have to make this gain margin come near 18. Sorry. I think gain margin is 10, right? That's what your requirement. Your phase margin should be greater than 50. At least it should be 50. That's how you have to. Now you want to increase your phase margin from 18 to 50 and decrease your gain margin from infinity to 10. That's how you want to design a compensator. So what is the next step? Once we found this desired characteristics, now we will calculate how much you want to jump from. So your current gain margin is 18, required is 50. So 50 minus 18 is around 34. 34 degrees you have to increase in the phase margin. But we will
30.
32, awesome. 32 degrees we have to increase in your phase margin. But we won't, like, since it is a trial and error method, we won't do exactly as it is. We will have some 5 degrees here and there compensation. So I am going to consider 32 plus 5 to make it robust. I say that we need 38 degrees to increase so far. Okay. This is the base we have set up. Now we found, like, we have a deviation of 38 degrees in phase margin. First, we will work around it. For finding that values, look, okay. First of all, how do we name this 38? That is the deviation between your desired and your actual phase margin. That we call it as phi m. Phi in the sense phi symbol. You know that, right? I cannot go back to iPad and laptop, so I'm typing it here. This we call it as phi m. Phi is the scientific symbol phi. So this is the deviation between your required and the available phase margin. Now, since I want to increase this, I am going with the lag compensator. No, not lag, lead compensator. Okay. So in order to increase the phase margin, I want a lead compensator. how the lead compensator will look like? 1 plus S 1 S plus 1 by T divided by S plus 1 by alpha T, where alpha should be in between 0 to 1. So that's how my lead compensator should be. So now, the relation between your phi m that you found so far and the alpha in your lead compensator can be represented using this below formula. That is sine of phi m, phi underscore m is equal to 1 minus alpha
Ma'am,
divided by.
compensator is spelling is wrong. Compensator.
Ah, okay. That's fine. That you understood is that's 1 minus alpha divided by 1 plus alpha. Okay, fine. This is the formula that relates your deviation phase margin and the compensator variable alpha that we want to design. If I want to design a compensator, I should find the alpha, right? So that's how we find alpha from the existing variable, that is phi m here. So now, if we calculate this, I know phi m. I need my phi m is 38, right? So here it will be 38 equal to 1 minus A. A is alpha here divided by 1 plus A. So this can again be written using 38 plus 38A equal to 1 minus A. Again, this will be 38 plus 38A. I'm writing it calculate 38 minus 1 plus 38A plus A equal to 0. Right? So this will be 39A equal to 37. Correct? So my alpha will be around 37 by 39. 0.94. How come? 1 minus A by 1 plus A. Okay, 0.94. 38 plus 38A. I'm not doing any mistake here, right? 38 minus 1. 38A plus A.
No, calculation is okay.
This was okay only. 37 divided by 39. So, 37 will be greater than 1, right? Okay. Your alpha will be 0.9. So let's keep your alpha as 0.9. Okay. Right. That's how we find a compensator. Now we will use this. We won't use as it is. We will convert this to decibels because in Bode plot we will use it as decibels only. And the next thing is you want to find this. The next step is to find the t value. So in your compensator, alpha you know, but the next variable is t that you don't know, right? So how can we connect this with the alpha and t? That's what we have to find. First, we need to find that. First, we need to find where is your maximum phase lead is acquiring. So to find the maximum phase lead, it will acquire at the crossover frequency. How to find the crossover frequency is 1 by root of SQRT, that is square root of your alpha, that is A. So it will give you 1 divided by root A root of 0.94. So that will give me SQRT of 0.94, 0.96. So 1 divided by 0.96 is 1.04. So it will happen at a frequency that is new gain crossover frequency, it is 1.04. So you have to look for this frequency to find your new gain crossover frequency. So if I plot this Bode, if I find it around one frequency one, which it is coming. It's coming around six radians per second. That is your frequency. Yeah, around like approximately around it. Okay, like we will do this again in detail. I wanted to show it in write all the formulas in iPad. We will do this on Monday. Okay. Before that, since we release the design assignment, I want to show you how you can submit your design assignment in the first place. Design using root lookers. So here you have this design assignment. If you open this, see, this is your design assignment that has been released. The deadline is till 20th April. Please don't take it by 19th night. Take it few days before, like at least 2-3 days to for you to understand and do everything by yourself, because there are many things to like put answer for. If you open this design assignment, use the following link to view your data. So if you don't have MATLAB, you can install it via this link given here. Otherwise, you can use online MATLAB platform. That is also fine. The next thing is each students get a different data sets. We are fixing unique data sets for every student. So you will get your own data set that won't mix with other people. Even though it mismatches, by designing your compensator, since I taken that 5% here and there, it won't be too identical between you and somebody else. So that is the point of having this design assignment.
Ma'am,
Then,
there is two rows for data.
I
Which
will
one?
share. So if you have this, what are you saying as two rows of data? Oh, here, which one you should take? Are you asking which column you should take?
Yes, ma'am.
Here you have been assigned, right? So look for your roll number and you take that data near to your roll number. These are actual data that we already generated, but people might think that we are assigning like rough or hard, difficult data for people we don't like, right? There are politics like that. So we are using a random data generator to assign randomly to students. There is no ambiguity in assigning the data. To make it transparent and straightforward, we are doing this. That's it.
Okay, ma'am. Okay.
According to your roll number, you take your data, assigned data, that is A, X, and Y. This A and X and Y, what it is have been explained here. Save the values A, X, and Y assigned for your lot or the roll number. And in this question, you will know what is A. So A is this in the transfer function, and X is your steady state error value, and Y is the settling time value. Now you understood all A, X, and Y, right? So the
Okay.
next thing is this you get the data. Then the next thing is you will see this problem, substitute all your values here. For example, consider a closed loop system with open loop transfer function given this. So you will apply your A here and your transfer function will be everything known to you, right? And you have find the value of K for uncompensated system has a maximum peak overshoot of 16. So use the e power minus tau pi divided by root of 1 minus, sorry,
Yes,
not
ma'am.
tau, that overshoot formula. And find this, you know, the overshoot left hand side 0.16 and right hand side is this transfer function known to you except the k, and find the k value. Then calculate the settling time and the steady state error for that k value you found. That can be done either by hand, by using the formula 4 by zeta omega n. Otherwise, you can use it MATLAB also. We are recommending you to use MATLAB. Find how to find the settling time and overshoot for a steady state error for any problem in MATLAB. There are plenty of materials available. You can check website and you can use that. No problem. And then comes the design aspects. Find desirable, suitable cascade compensator. Cascade means putting two compensator together, but you don't necessarily put two or three compensators. For some data, since we have assigned unique data set to everybody, some people might get one in one compensator, you will get the results. Some people need to put two compensators in like series, one into another to get the desired specification. So we have commonly mentioned that suitable cascade compensator, it can be one or multiple. It's according to your convenience. Just see with one compensator whether you will be able to achieve the end results. Otherwise, you do multiple times. That's it. So the design should follow the steady state error for unit ramp reference, E of SS should be less than your X value, and UC is the uncompensated system. So for the here you will find the steady state error for the ramp reference in MATLAB, right? This is your ECES UC that you will put as a upper bound into your X. For example, if my steady state error for the ramp reference of the system I found here with K value is zero point 0.1, let's take, and my X is 10, then this value should be your overall steady state error should be less than 1. That's how you have to calculate your X into your steady state error for the uncompensated system you found from this point. The next design criteria is that your compensated system should have a peak overshoot equal to 16 or nearly equal to 16. Try to keep it like that. The third criteria is your settling time should be less than your Y percentage you take from your Excel sheet. Okay. And this settling time should be less than or equal to Y into your settling time of the uncompensated system that you are finding here. So you will take data from your Excel sheet A, X, Y, and you will find a set K value first and put a value here. You will get a whole new system. After finding the K, you are finding settling time and steady state error. Now, the new compensated system steady state error should be your X into old one. New settling time should be less than your Y into old one. That's how it is. Clear?
Yes, ma'am.
Instead of giving your settling time should be less than zero point 0.1, since we are using unit data, we are mapping it to it. That's it. There is no very big challenge here. And then use MATLAB, online MATLAB. If you come here to the submission guidelines, there is a link like answer template. This we made to make it easy. Some people don't know what to include and how to write. So that's why we gave this
Yes, ma'am.
guidance. Please follow this template. So here we have asked open loop transfer function with a value. So first what you are doing here, you are wait. Here you are finding your a from your sheet, right? Write the transfer function with a. That's it. You will get 1 mark for this kind of. Saying for example. Then you find the k value, put the k value here, you will get mark for it. Find the settling time of the uncompensated system, you will get mark for that. And steady state error for the this system, put it here. And then draw a root locus for the original system you found k with k and a value, and attach the figure here with the overshoot and on all the markers.
Ma'am, from MATLAB.
Yeah, from MATLAB. Paste the figure here in this space.
Okay, ma'am.
And then you say what is your updated steady state error should be. This the value you have to enter here is x into this value found here, right?
Okay, okay.
The
Yes,
value
ma'am.
you write here should be y into this value here. That's it. You will get marks for all these things. Just simply, if you don't even use MATLAB, you will get marks for all these things. So please submit this, and whatever way you could do that, at least do that basic things. Okay. Then you design a compensator as Jada's explanation, or you can watch YouTube lectures, source videos are there, professors' videos are there, and design the transfer function of the compensator, and then your original transfer function into this transfer function. You write here, and this is to be drawn, this root locus to be drawn for this GS into G, not only for G. Okay. It's a root locus of the compensated system, not for compensator. So it should be G and GS. Your root locus should be plotted for the G into GS. That's it. And then closed loop step response. It's just step of your systems, G into GS. That will give you the step response. Attach the figure below here. And then you write what compensator you choose, why you chose that compensator. Everything carries marks. If you put it like a lag compensator correctly, you will get some marks. Something I'm saying like that. Okay, this is a simple assignment that will help you score good marks to increase your grade jump from one to another. Okay, so please utilize this design assignment. Put your confusion or any queries in the discourse. We will answer them.
Ma'am, submission format A4 in 4
Mm.
submission format. Submit your work as uh,
Two separate files in G form, right? So why I said that is, if you go here this is submission drive link is given, but actually it is G form. That is linked to drive. So give your email here, name here, roll number here, and then the PDF. This one you have updated your marks, right? You can use either your laptop's Word document, otherwise, you can use online docs also. This cannot be edited, so don't request edit access. Just go here to the file, download, and you can download this empty file as docs. And then edit in your system or upload this again to your mail ID's docs online. And then you can edit. After editing, just fill all the details, then again download it, save it as PDF, and upload it here in the SAT file.
okay, ma'am. Now I understand.
Yeah. Then again,
Okay,
you will use some MATLAB code for this, right? Upload that MATLAB file entirely here.
okay,
That's it. And then you submit.
okay, ma'am. Okay, ma'am.
That's how the submission should be done.
Okay,
Entirely. We made it as easy as possible for students to access it. If you still face any difficulties, let us know in the discourse. We will help you. Okay.
okay,
Okay.
ma'am.
If you, I'm leaving now. We will discuss further things in the discourse, and I will continue that problem by Wednesday.
Okay, ma'am.
Okay. Thank you.